We're in Chapter 18, which is sampling distributions for proportions. There are several definitions that we need to go through, the first being population distribution. This is just the graphical display of data from a population, so this is just whatever raw data you get from a population and you put it on a graph. Then we have sampling distribution. This is the distribution of values taken by the statistic in all possible samples of the sample size from the same population. So how this differs is in sampling distribution, you would take data from all the different samples that would be possible as long as those samples are the same size. So you have data from this sample of size 10, data from this sample of size 10, and data from this sample of size 10, and you put that on a graphical display. Our next definition is a statistic. A statistic is a numerical value computed from a sample, and then we have a parameter, which is a number associated with the population, and it is generally assumed that the value is fixed, unchanging, and unknown. So the way that I remember the difference between a statistic and a parameter, I relate statistic. It starts with an S, and then a statistic comes from a sample. And then parameter starts with a P. It's associated with the population, which also starts with a P. And again, the parameter is sometimes unknown because sometimes the population is so big that we don't know the actual mean and standard deviation. So the observed value of a statistic will vary from sample to sample. This fact is called sampling variability. So if you think about it, it makes a lot of sense. If you are taking a bunch of samples from a population, you're not going to get the same. Let's say we're talking about people, we're sampling Oak Ridge High School, and I decide to take 10 people here, sample, 10 people here, sample. The results are going to vary a little bit, but overall, when you put them all together, they should average out to be the same as your population mean or standard deviation. But just know that a statistic will vary, unlike a parameter where the parameter is unchanging. We've talked about describing distributions before, and we're just going to move on to describing sampling distributions, which is the same thing. We still need a center, shape, and a spread, but the way you find it is a little bit different than what we're used to. So the sampling distributions can be described by the center. The center is going to be our mean, and it's represented by the formula mu p hat equals p, and what that stands for is the mean of our sampling distribution is equal to the proportion of the population. And so let's use the example of freshmen at Oak Ridge High School. If I say that 25% of students at Oak Ridge High School are freshmen, that is my P, that's my population proportion, so I would use 0.25 as my mean. For this spread, you're going to use the formula sigma p hat, so this is the standard deviation of the sampling distribution, is equal to the square root of P, which would be 0.25 in my example. So P times 1 minus P divided by N. You may also see 1 minus P written as Q, so sometimes the formula looks like square root of P times Q divided by N, and you have to make sure you square root all of that. And then we have the shape. So the shape's going to be the same as the population for a small sample size. So if you have a small sample size, the shape's going to be the same. So let's say that I said the distribution was skewed to the right. Then your small sample size is going to have a skewed right distribution or skewed right shape. And then it will be approximately normal if there is a large enough sample size. And how you determine if there's a large enough sample size is you need to do N, so your sample size times P. All right, so sample size times the proportion. In this case, it would be 0.25. It has to be greater than or equal to 10, and then you're also going to check that N times 1 minus P, so in this case it would be N times 0.75, that has to be greater than or equal to 10. And so if those conditions are met, then that means that your sample size is large enough to be normal. When you're asked to calculate probabilities involving sampling proportions, it's different than calculating probabilities that we've done already with normal CDF. You're still going to use normal CDF, but there are steps you've got to go through. You have to first state the mean and standard deviation, and then you're going to determine if the sampling distribution is approximately normal. If it's not, there's no reason to move forward because z-score calculations aren't going to work if your sampling distribution isn't normal. And then the third step is writing a probability statement with z-score Z-score calculations. And then the fourth step is to calculate the probability using normal CDF. And we've done normal CDF with chapter 6 with just regular probabilities and Z-scores. So I like to separate my paper into 4 pieces just to make sure that I get all 4 of those steps, and I will show you on the next slide how to do that. All right, so in this problem it says in a large high school of 2,500 students, 21% of them are seniors. A simple random sample of 150 students is taken and the proportion of seniors is calculated. What is the probability that the sample will contain less than 15% seniors? Whenever I look at this problem, I see it's asking what the probability is, and I know I'm going to need to use norm CDF. And then I see that I'm given a proportion, so that's what tells me that I'm going to do proportions. And then it also says that I take a simple random sample of 150 students. So I see that it is a sampling distribution problem for proportions because I have a sample and I have a proportion. So remember that the main step, the first step, so number 1, is going to be to write down the mean. So your mu p hat is equal to your p, and that's just the formula here. Let's make sure you can see that. That's just the formula. I know that my mu p hat is equal to my population proportion, and my population proportion is 21%. So 21%. Right? And then I need to find my standard deviation. The formula for standard deviation is sigma p hat equals the square root of PQ over N, where P is this proportion here, my Q is 1 minus that, and then N is my sample size. So this is going to be the square root of 0.21 times 0.79 divided by my sample size, and my sample size is 150. All right, so I'm going to take a minute to calculate that. All right, so what I make sure to do is I multiply this, divide by 150, and then I square root it at the end. And I get a standard deviation of 0.03326. Right. Your second step is going to be to verify that the conditions are met or that the sample size is large enough. And so remember, we need to make sure that NP is greater than or equal to 10 and that NQ is greater than or equal to 10. So this is my second step. And then to do that, you do your sample size, which is 150, times your P, which is 0.21, and then we are going to make sure that is greater than or equal to 10. So 150 times 0.21 is equal to 31.5, which is greater than or equal to 10. So that one works. And then you're going to do 150 times 0.79, 150 times 0.79 is equal to 118.5, which is greater than or equal to 10, so that condition's met. And I'm just going to write here that sampling distribution is approximately normal. All right, and for your third step, and okay, so the reason I did this was it just tells me a random sample. It doesn't tell me anything about the population. If it would have told you that the population was normal, then you could have just written here that the population was normal. But since that it didn't specify, I went ahead and checked that condition. All right, and then the third step is to write the probability statement, and I will do that in the next video. This video is going to cover steps 3 and 4, so if you haven't watched steps 1 and 2, go back and do that. Remember, step 3 is writing the probability statement with the z-score calculations. That probability statement is going to be the probability that P is less than 0.15, so that's what it's asking. The probability that it's less than 15% seniors is equal to the probability that, remember our z-score calculations, it's x minus mu divided by the standard deviation. So 0.15 minus 0.21 divided by the standard deviation that we calculated in step 1. So 0.03326. All right, equals the probability that z is less than negative 1.804. All right, so whenever you calculate, when you do 0.15 minus 0.21 and divide all of that by 0.03326, you get a z-score here. And then our fourth step is that we actually do the calculations with that z-score. So we're going to use NCDF. So fourth step is NCDF. And then it wants to know less than. So in a less than, remember your distribution, your z-score distribution, less than would be shaded to the left. So that's going to be going towards negative 99. So we're going to do negative 99. You always put the lower number first, to our z-score of negative 1.804. All right, and I'm going to calculate this. Let's review the calculations. All right, let's see if you can see this. We're going to go, I already have it on here, but toolbox, probability, cumulative, normal, and you should see NCDF, and we're going to do negative 99 to negative, where's my negative? 1.804 equals, and then that gives me a probability of 0.0356. And then the last thing you need to do here is just write our statement answering the question. There is a 3.56% chance of, and we're just answering the question, of a sample containing less than 15% seniors. All right, and then something that would sound a little bit better even is there's a 3.56% chance of a sample of this size containing less than 15% seniors. All 4 of these steps need to be completed to get full credit for calculating the probability of a sampling distribution of proportions problem.